Welcome guys in this video session. So in this video tutorial we will discuss a numerical problem on equalizer in the wireless communication system. So before starting the video I want to tell you, please subscribe my channel if you have not subscribed yet, and press the bell icon to get the new video notification on the channel. So let's start the video. So guys, in this numerical problem, let's understand this numerical first. So for an equalizer, guys, I one more thing I want to tell you. If you have not watched my previous video of equalizer, then please watch that particular video to get the idea about the equalizer. So please watch that particular video. I will give the link of that video in this description. So let's start. For equalizer, if the carrier frequency FC is 900 megahertz and maximum Doppler shift is 66.67 hertz, then we will calculate here the different parts of this numerical, different parameters here. So firstly, what is Doppler shift? So Doppler shift is nothing but it is basically the time varying nature of the frequencies in the channel. So that is called the Doppler shift, and Doppler shift and Doppler spread is both are same, but difference only is there. The higher frequency of the Doppler shift, that is the known as Doppler spread. So what is Doppler shift and Doppler spread? Basically, if we take an example as in case of ambulance siren, when any ambulance, when it is playing their siren and passes from us, then when this ambulance is coming toward to us, then it's playing siren and we hear the sound of that particular siren. That is, the sound is increasing and coming toward us. So when the ambulance passes us and move away, then the speed the volume of that particular siren is decreasing slowly. So this is the variation in the sound frequency, so that is known as the Doppler shift, Doppler spread. That is called the Doppler spread. So the higher frequency that we have here of that particular siren of ambulance, so that is the Doppler spread. So basically here we can understand this, the variation in the frequency, basically that is known as the Doppler shift here. So here the maximum Doppler shift value we have considered 66.67 hertz. So we will calculate the following parts of this numerical. So let's understand one by one. First part is here, the calculate the maximum mobile velocity of the given Doppler shift. So here the Doppler shift is given 66.67. So here we will calculate the maximum mobile velocity. How much velocity with the mobile is moving, basically what is the maximum speed of the mobile when that particular user observe this Doppler shift 66.67 hertz frequency. So this part in the first part, this is the first part of this numerical, and in this part we will find out this maximum mobile velocity. Then in the second part we will calculate the coherence time of the channel. Basically coherence time is the time where the frequency response of the channel is flat. The frequency of the channel is flat, so that is the time is the coherence time, that is known as coherence time. So in the third part, what is find the Doppler spread. So we will find out here the Doppler spread. Basically Doppler spread is the higher value of the Doppler shift. Here the higher value of Doppler shift is 66.67 hertz is given. So we will easily write here, or we will consider here 66.67 hertz as a Doppler shift, but we will solve this with the formulas here, and in the fourth part, assume the symbol rate is 24.3 kilo symbols per seconds here. So there is a basically a transmission of any signal and or a message. So the transmission symbol rate is 24,300 symbols per seconds are transmitted. Here what are the symbols? Basically symbols are nothing but these are the combination of the more than one bits that's become a symbol. So here the symbol rate is 24.3 k or 24,300 symbols per second. Then calculate the maximum number of the symbols that can be transmitted without updating the equalizer. So as we all know, in the equalizer, basically equalizer is behaving like a filter in the receiver, filtering the receiver to reduce the interference from the transmitted signal. So basically equalizer is the part of the receiver. So in the equalizer there are the different weights, and according to the every transmission and reception of the signal on the receiver, it will reduce this remove the errors from the data, and it will correct the data and get the output, desired output. So before the equalizer, the data that is received in the receiver, that is the basically we will find out before the basically the input data of the equalizer. So how much symbol rate is there, maximum symbol rate is there of the transmitted data that is in the receiver. So that we will here calculate in this fourth part. And in the fifth part, here assume there are the 5 delays element in the equalizer, as we all know. So in the equalizer there are the different delay elements. We will discuss diagrammatically in the fifth part here, and with every delay element have the 10 microsecond delay. So we will calculate the maximum number of the taps, how much number of the taps are there. And in the last part, calculate the maximum multipath delay spread here, how much delay is in the fifth part. So the total delay spread we will calculate in the sixth part according to the part fifth. So fifth part we will discuss diagrammatically and then find out the maximum multipath delay spread that could be equalized in the sixth part. So let's start to solve this numerical problem one by one. So here the first part, firstly we will solve this first part. So first part here the given values are basically the carrier frequency FC is 900 megahertz, or we can write here 900 into 10 raised to power 6, and the Doppler shift FM is the maximum Doppler shift frequency, that is 66.67 hertz. So these things are given here. So here we will find out in the first part the maximum mobile velocity of the given Doppler shift. So we will find out the maximum mobile velocity here. So here use the formula for the velocity V. So use the formula velocity V is equal to basically the maximum Doppler shift frequency into lambda. So here the lambda is a wavelength, so we replace with lambda here the speed of light over the carrier frequency. So here lambda is basically c upon fc. So substitute here fm into c upon fc. This is the formula. So put the value here. Fm is 66.67 multiply the speed of light is 3 into 10 raised to power 8 meter per second divided by carrier frequency is 900 into 10 raised to power 6. This is also in meter per second here. So when we calculate this, then we will get the 22.223 meter per second. So here this is basically a velocity, mobile velocity in meter per second. So as we all know, the speed of any object or anything that is in the kilometer per hour. So we will convert here this in meter per second into kilometer per hour. So here in the 1 hour there are the 3600 seconds, so we will multiply this to 2.223 multiply 3600, then we will get this is in the 8000, basically 2 something like this value. So here this is approximately equal to 80,000 meter per second. This will, if we here this is the 80 this hour, here meter per hour. So here if we convert this meter into kilometer, then 1000 meter, so that is the kilometer, 80 kilometer per hour here. So here the speed of the mobile or maximum mobile velocity is 80 kilometer per hour when it observe this the Doppler shift 66.67 hertz. So this is the solution for part first. So guys, let's move to the next part. Here in the next part calculate the coherence time of the channel. So what is the coherence time of the channel? We will calculate here. So basically coherence time is the time basically when the frequency response is flat in the channel. So that is called the coherence time basically. So coherence time represented by tau of c. So this is basically inversely proportional to the 1 upon f c basically, or 1 upon frequency. So here, but the formula for find out the numerical solution, so that is the tau of c, that is equal to 0.423 divided by Doppler, maximum Doppler frequency. So this is the formula. So here we will simply substitute the value 0.423 divided by 66.67. so then we will get 6.34 millisecond. So this much of the coherence time is there when the Doppler shift is 66.67 hertz. So 6.34 millisecond coherence time means for this much of time the channel frequency response will be flat. So let's move to the third part here. So in the third part we will find the Doppler spread. What is Doppler spread? So I have already told you Doppler spread. So Doppler spread is nothing but the Doppler spread that is the highest value of Doppler shift. So here Doppler spread that is equal to FM. FM is the Doppler shift here, that is 66.67. Let's prove this. This Doppler shift is equal to this Doppler shift. FM is Doppler shift and Doppler spread is simply Doppler spread. So we will represent here the Doppler spread BD. If we represent this, then that is equal to FM. So let's prove this with the help of formula, that is a nu means velocity, mobile velocity, that is multiplied with carrier frequency over the speed of light. Basically this carrier frequency is divided into the signals in the speed of light. So here the mobile velocity in meter per second is how much, that we have calculated basically in meter per second, this 22.223 meter per second. Here 22.223 meter per second. Why we have taken as meter per second? Because the speed of light is in meter per second, that is multiplied with 900 into 10 raised to power 6 meter per second divided by 3 into 10 raised to power 8 meter per second. And when we calculate this, then it is approximately 6.66, so that is or 67 hertz. So this is the Doppler spread basically. So here this is the highest value of the Doppler shift, so that is equal to the Doppler spread. So this is the Doppler spread. So let's move to the fourth part of this numerical. Here in the fourth part, assuming the symbol rate is 24.3 k, symbols are 3000 symbols per seconds. This is a symbol rate, and we will calculate the maximum number of the symbols, how much maximum number of the symbols that can be transmitted before the updation of the equalizer. Means before the equalizer, the data in how much symbol rates are used to transmitting the data in the receiver before the equalizer. So in the receiver, we will here calculate the symbol rate, maximum symbol rate. So in the fourth part, here let's move to the next page. So here fourth part, in the given the symbol rate is 24.3 k symbols per second is given. So this is approximately equal to 24,300 symbols per second. So this much symbol rate is given, so we will find out the maximum symbol rate, how much the maximum number of the symbol rates where the data is transmitted before the equalizer updation. So the maximum number of symbol rates we will calculate. So this represent with the NB. If we represent this NB, maximum number of the bits, and so the more than one bits when we combine, that create a symbol. So here the NB, the total maximum number of the bits, so that is equal to basically the symbol rate. This RS represents the symbol rate, that is multiplied with the coherence time, tau of C. So here symbol rate is 24,300 symbols per second multiplied with coherence time. How much coherence time we have calculated in this second part. So here the coherence time is 6.34 millisecond. So 6.34 millisecond, this. So here 6.34 millisecond. So symbol per second. If we convert this millisecond into symbol per second, that is 0.00634. This is 24,300 multiplied 0.00634. So when we multiply this, then the total maximum number of the symbol rate, that will be equal to how much? This will 154 symbols per second. So the transmission of the data with the maximum symbol rate, that is 154 symbol per second to the receiver before the updation of the weights in the equalizer. So the 154 symbols per seconds, these are the maximum number of the transmission of symbol rate. So let's move to the part 5th. Assume there are the 5 delay element in an equalizer with 10 microsecond delay in each. So calculate the maximum number of the taps. So let's solve this diagrammatically. Here what are the maximum number of the taps are there? If there are the 5 delays element and each have 10 microsecond delay, then how much number of the taps? That we will solve here. So diagrammatically here in the equalizer, these are the delay elements, and this is input, this is output. So each have a 10 microsecond delay, 10 microsecond delay. So these are the taps. Here means these are behaving like a channel, so that are connected with between the delay elements. So here the total number of the 5 delay element and 6 taps are there. So for finding the taps, total taps are equal to delay element plus 1. This is the formula for finding the taps. So total number of the taps that are equal to delay are the 5 delay element plus 1, that is equal to 6. So there are the 6 channel taps are there. These are the taps. These are the taps and these are the delay elements. So this is the part 5th, and let's move to the last part of this numerical. Here assume here the calculate the maximum multipath delay spread that could be equalized. How much maximum multipath delay spread that could be equalized? So here according to this 5th part, here let's move the 6th part. According to this 5th part, here the total number of the delay elements are 5 and each have 10 microsecond delay. So delay spread that is the delay element multiply delay total. So here the total delay spread that is equal to 10 multiply 5, that is 50 microsecond delay. 50 microsecond delay. Here the total 50 microsecond delay would be equalized. So excess of this 50 microsecond delay could not be equalized because there are only 5, because there are only these 5 delay element and each have 10 microsecond delay. So if we calculate this, the total number of the delay spread is 50 microseconds. So only 50 microsecond delay could be equalized. So that's all in this numerical problem, guys. So if you really get something from this numerical video, then please subscribe my channel, like the videos, and guys, if you have any query regarding this numerical video or any video, then please mention in the comment section.